today I'm just going to go through this Jupyter notebook that we created for the MMSA testbed. This is the first example, so it contains very limited set of analyses for now, but we are continuously working to grow it further. So I'll just first start to explain what this contains, and then we can go through the notebook itself. So for now, the notebook focuses on the probabilistic damage and functionality analysis of buildings and supporting physical infrastructure in Shelby County, subject to a scenario earthquake. The things that we have is part of the built environment. Then we have the hazard model for the earthquake, the damage models, and then the functionality analysis. So when it comes to the building data set for Shelby County is actually one of the first data sets that are available in INCORE since a long time. It comes originally from Mavis, includes residential, commercial, and industrial buildings. The water network topology is also inherited from the Mavis as well as the power network. The sources of these network topology, I think, is first started from the work of Professor Shinizuka and then modified by, I think, Professor Osorio. That is a simplified topology, and that is the one that is available that was available in Mavis and is now also available in INCORE. So the hazard model is GMPE, also from Mavis, and the damage model for buildings, there is fragility curves from Mavis, and for water network, there are fragility curves from HAZUS, and same for the power network as well. When it comes to the functionality model, the high fidelity models are not yet in INCORE. So for this, for the purpose of this notebook, we are only as a placeholder, we are only putting the connectivity based analysis for water and power. So now I'll go to the notebook itself. So we starting from some initial introduction of what this includes, and then name of the people who worked on it. It was Armin, myself, and Professor Gardoni. And then some background on the demographics of the Shelby County and the requirements of what PyInCore version and PyInCore base version required, and some of the packages that we use in this notebook. So you all are, I think, familiar with the regular imports that are required when we use INCORE. In addition to that, we are using the NetworkX library, which is a pretty basic but very useful package in Python that can be used for doing some connectivity-based analysis on network datasets. And for some probabilistic analysis, we need the SciPy stats module, and we're using the Poisson process and the Bernoulli distribution. Okay, so we start with defining the characteristics of the scenario earthquake. This is a traditionally used earthquake scenario that has been used in the scenario earthquake analysis for Shelby County. And also, if you look at the May Center website, you'll find that this is the scenario that was developed for the whole Central or Mid-America zone. So any region of interest that lies within, say, Mississippi or Tennessee can use this earthquake scenario, or these are basically the scenario that is used by even the state emergency management agencies. So these are some of the characteristics of the earthquake that I printed out here. Then we do the building damage analysis. The data set is already available in INCORE, so we download that. We set the mapping ID, which defines which fragilities this is using. We set this is the default fragilities basically that are inherited from Mavis, but you can also select the HAZUS fragilities. And just a look at the typical data that is available for each of the building. And then we plot the inventory, and we are plotting here the different structural types. You can see that it includes uh, reinforced concrete buildings, wooden buildings, and unreinforced masonry, and sort of other type of things. But most of the structures are wooden, which are residential, single-family homes, or other residential structures. We create this is a normal damage analysis for buildings in INCORE. We set up the parameters for the result name and the dataset ID and the earthquake ID and run the analysis, and we get the results. Now then we are plotting the most likely damage state for each of the buildings in this chart. But other than that, one of the things that we added was in visualization part. So although INCORE, the current INCORE based plots, they're useful, but in terms of how you can edit them, it's limited in some ways. And one of those ways is that we would typically like to plot multiple things on the same map. For example, if you're plotting a network data set, then I would like to look at the pipes and the nodes and the results relating to both in the same map. So we wrote a little function that actually edits available function in the PyInCore Viz library to do that. And we'll see how we can use this later on. For now, we plotted this the results for the building damage analysis. There is also a little piece of code here that modifies the labels for these, because the default labels are basically DS1, DS2, which are the damage states, but it doesn't really, they are not very descriptive. So if you would like to change how it's displayed on the map, you can use this code. And it basically says which the name of the damage state of each building. And for the May Center fragilities, there are 4 which are insignificant, moderate, heavy, and complete. Then we move to the infrastructure damage analysis. It's very similar to the building one, but it's just the mapping set and other things are different here. And we did that for water pipeline damage. We have the results of the pipeline damage. You see there are 2 or 3 different type of things. There are repairs due to PGV and due to PGD. The repair due to PGV or ground velocities are typically reliable, but so PGD, it's supposed to represent permanent ground deformation. And for that, you should be like anyone should be using basically the liquefaction susceptibility, and it is a more complex analysis. So I'm not super like these results. I'm not super confident about. I don't know how INCORE currently does this in the background, and so this part, the peak, the permanent ground deformation based repairs, I would like take them with a grain of salt. So for the purpose of this analysis, we only focused on the repair rate that is based on PGV, and those results make more sense. And move on to the water facility damage. Here, the data set that was available in INCORE had some discrepancy in the data. So we created a new data set and we modified those attributes there. And this has basically pumping plants and also tanks, and then junctions. And then we did the damage analysis for this. Here we plot this into using this interactive plot, which is based on IPy leaflet. Again, this is also part of the INCORE Viz library, but the functionality is very limited. So I didn't have a lot of time this time, but in the future, it would be interesting to work on these visualizations and make them more interactive and useful. I think for the purpose of regional impact assessment and resilience analysis, we can come up with 2 or 3 standard types of visualizations in the interactive version as well, so that it would be useful. And finally, this is plotting the results for the water network. And you see that the function that I showed earlier, how it's useful is currently, this is basically generating a figure that is almost report ready. So we have plotted the number of repairs per kilometer for the pipes, and the damage or the probabilistic damage or most likely damage state for each of the nodes, as well as just the normal location of all the junctions in the same plot. And then you can just directly copy this and directly use into some reporting document that you're working, or even for publications. Moving on to the electrical power transmission line and facilities. So for power transmission lines, they're typically considered to be not damaged in earthquake scenarios. Only the distribution part has some damage, and the substations are prone to earthquake damage. So we are just showing the topology for the power lines and doing the damage analysis for electrical substations. It's very similar to the water case. And we are again plotting the topology of these networks and then showing the result for most likely damaged state of the power substations in Shelby County, and then showing the topology of the power lines. Then the last section is about infrastructure functionality analysis for both potable water infrastructure and power. We wrote a little function again that actually reads the data from an in-core data set and creates a network data set that can be used in Network X. So we get the geodata frame from the currently available data set, and we create a Network X data set that can be used for connectivity analysis. We just use a multi-source extra path algorithm, which gives you the shortest path between a number of sources and any given node. And this is the baseline results for the undamaged network. And then we do a Monte Carlo simulation for the damage part to get the